Okay, so we're starting a new topic today, which is online algorithms. Until now, in this course, we've had algorithms which receive an input and compute an output. But crucially, they make their decision, they determine the appropriate output after looking at the entire input. So now we're going to study problems which are kind of ongoing, where the input arrives a little at a time. And each bit of input demands an immediate response. And this response has to happen before you see the rest of the input. Sounds like somebody's vacuuming, which is a good habit, but please mute if it's you. For example, we've got things like the stock market, right? I mean, if somebody gave you the entire trace of the stock market and said, what series of trades would make you tons of money, that would be easy to answer, right? The problem is that you have to decide on your trades, only knowing the stock market up until now. You don't know what it's going to do tomorrow, okay? A problem which arises in computing and which we will be studying is paging. So paging is what happens when you're trying to do a computation that takes more memory than you have on your computer. And so modern operating systems will manage that memory for you so that you can pretend that you have more memory for your computation. But that memory doesn't all fit in your actual memory. So the operating system takes care of moving some of it onto your disk and storing it in files. And then when you access a memory location which isn't actually in memory, the operating system has to fetch that part of your memory off of disk and bring it into memory so that you can look at it. This is called a page fault. Paging works with what's called a virtual memory. I think you've all seen this in 6004, right? It's larger than your real memory, and some of it is stored on disk or whatever your external storage device is. And the problem with these external storage devices is that they're slow. And so the operating system has to decide which virtual memory pieces to move to disk. The problem is that when you need one of those pieces, you have what's called a page fault. And you have to take the time to fetch that page back into memory so that you can operate on that piece of your virtual memory. And the problem is that these page faults are slow and they slow down your processing. So of course, if you knew in advance which memory was needed, then you would send to memory, you would send to disk the memory that you didn't need, right? But you don't know that, right? The program is running and you don't know what it's going to do next. So you don't know which memory it's going to need. And so you have to make this decision in the moment when you need to make room for something. What are you going to send from memory to disk? What are you going to evict? Okay, so the stock market and paging, they're both examples where it's pretty easy to know what to do if you have the entire sequence of actions ahead of time, but it's very challenging to decide what to do if you don't know the future. Okay, So we are going to want to design so-called good algorithms for these so-called online problems. Okay. So just to add some formalization there, we are going to model this as a input sequence, sigma, right, which is a series of symbols or inputs or whatever you want to call it. And the idea is that after each input, you have to produce an output or perform an action. And you want to optimize your cost, right, of all of these outputs or actions. Okay. And I'll refer to that optimal value as C sub min of the sequence sigma. And it's often easy to compute. C min of sigma, given the whole sequence. But we have to act after each symbol. And so we might not be able to, we can't plan against the entire sequence. Okay. So let's look at a particularly simple example of this to get some of the ideas. Okay. And this is a problem which was invented to look at online algorithms called the ski rental problem. So the idea is, you've decided to take up a new hobby. And of course, it needs to be a hobby that does not involve getting close to any other people. So skiing is a good one, right? Outdoors, far apart. You're not supposed to run into anybody. So promising. As a hobby, you can ride the chairlift in solo instead of in pairs. The question is, if you've decided to dive into skiing, you can go to the ski resorts and you can rent skis. It's cost you a certain amount every time you go. Alternatively, you could buy skis, right? So we can formulate this by sort of setting the units appropriately. Renting the skis will cost 1 unit. And in comparison, buying the skis will cost some amount T, which is presumably quite a bit larger than 1. Okay. And the question is, what should you do? So you wake up in the morning, you decide it's a good day to go skiing. Do you rent or do you buy? How do we decide?
Probably you start off renting, but if you find that you're renting a certain number of times, then there's some threshold. You say, the past predicts the future. I'll probably continue skiing a lot. Let's buy.
Ah, well, the idea that the past predicts the future is very optimistic, right? Because there's this guy named Murphy around, right? Obviously the moment that you buy skis, you're going to fall and break your leg, right? So, I mean, it is possible. You can think about a probabilistic model of your inputs, right? You can say, well, here's my distribution over possible sigma sequences, and I will develop an algorithm that has good expected performance. But that involves a much too optimistic perspective, given what we've seen in 2020, right? We need to be much more pessimistic about everything going wrong that can go wrong. And we want to prepare for that kind of bad outcome.
Wait, is T given to us?
Yes. So we know the price of renting and we know the price of buying. But that doesn't tell us this key question, right? So the point is, if you know that you'll ski once, then you should rent. If you know that you're going to ski often, then you should buy, right? But we don't know, right?
I mean, if you want to compete against any possible outcome, we should buy a ski.
Good. So can you elaborate that argument? You say if we want to compete against any possible outcome, we should buy the skis. So so let's turn that around. What happens if we never buy? Right?
Then in the worst case, like we have to pay infinite amount of money.
Yeah, we could, right? We could become the next gold medal Olympian skier and end up spending an infinite amount of money on skiing. So there's this terrible outcome, right? Where if we never buy, we're going to spend unbounded amount. Okay, so that says we should buy, right? But what's the problem if we just follow that advice and buy?
Well, if we only ski once and like we waste a lot of money.
Exactly. We all have these, momentary passions, and it's really cold on the ski slopes. So we may just, ski once and end of story. And we've just blown a lot of money on one day, right? And the problem is we can't know what's going to happen. So how do we even assess what is a good algorithm? Or how do we measure the quality of an algorithm? Right? So, one problem is, the most obvious thing to do would just be to look at the cost of your algorithm on the sequence, right? The problem is that sometimes there's no good cost, right? Sometimes the cost is always terrible. Right? If you put some money into the stock market and then the stock market just goes down every day, there's really no way for you to do well, right? If you have a paging problem, right? If you have a computer that's using a large amount of virtual memory and the computer just keeps on fetching new memory, well, you're just going to keep having page faults. There's nothing that you can do, right? So it doesn't make sense to just look at the cost of your algorithm in the worst case, because it's always going to be huge. So our goal is going to be to compare to the best possible outcome given the particular sequence sigma. Okay, so in particular, we define an algorithm to be k-competitive on sigma if the cost of the algorithm on sigma is at most k times the cost of the optimum for that same sequence sigma. And we define, and we say that the algorithm is k-competitive overall if it is competitive for all sequences sigma. Okay, so we're looking at sort of the ratio of our algorithm's cost to the cost of the clairvoyant algorithm that knows the future. Okay. And why do we look at a multiplicative ratio? Well, kind of for the same reason we looked at multiplicative ratios for approximation algorithms. You can define additive competitive ratios, but for most problems, they don't exist. there tend to be these amplifications that that mean that you can't actually achieve any additive competitive ratio. So we're going to jump straight to thinking about multiplicative competitive ratios. Okay. I'm also going, sometimes we also ignore edge effects. So we say that an algorithm is asymptotically k-competitive. If for any sequence, my cost is at most k times the optimum plus a constant. So, you know, if my algorithm is, you know, at most 7 times the optimum plus an extra $1, well, as the cost grows, that extra $1 doesn't matter, and so I won't worry about it. Okay. So with these definitions in mind, can I come up with a competitive algorithm for ski rent? Okay. Oh, and I should also add that K is just known as the competitive ratio for obvious reasons. So can I do a competitive algorithm for ski rental? Well, we've already started thinking about this, right? So we considered the always rent algorithm, right? So is the always rent algorithm competitive?
No, because your cost could go to infinity. Whereas like in the, I guess like when the number of times you ski goes up, the optimum would be T, but like the actual cost would go to infinity.
Exactly. So the problem with always renting is that I'm going to end up spending an infinite amount of money, whereas opt is going to, is at worst going to spend T by buying skis, right? So this is not a competitive algorithm. Okay. What if we buy immediately?
Is T competitive?
Right. So we're going to spend T, but the optimum algorithm might only spend 1 if we only go skiing once. So that's T competitive. And, you know, since T is probably quite a large number, that's not very good. So what are our other options? What's the design space of algorithms?
What you can wait until n number of times you went skiing and then buy the skis then.
Good. So basically there isn't a lot of flexibility here. Basically, you know, every time you wake up, you decide to go skiing, you have to decide whether to rent or buy, right? And of course, once you buy, you're never going to rent again. So, you know, the space of algorithms is that you rent some number of times and then buy. So maybe I'll rent for D days and then buy on day D plus 1. Okay. So we need to analyze this algorithm. We need to understand what is the worst ratio that we're going to achieve, which means we need to find the worst sequence for this algorithm. Now, what is our space of sequences? What are the inputs that we have to handle?
It's just like how many times you go skiing.
Yeah, the number of times you go before you break your leg, right? Okay. So let's think about that. Let's sort of imagine some D. We won't specify it yet, but you know, once I fixed a D, let's think about what happens after I fixed D, right? So I'm going to be renting for the first D days, right? So what's the adversary going to do? Well, the adversary is either going to rent all the time or buy right at the beginning, right? Because it knows the future. It knows if I'm going to ski more than T times, I should buy. And if I'm going to ski less than T times, I should rent. Yes? So I'm renting. Maybe the algorithm is renting. And as long as that happens, we're completely in sync, right? And, you know, our ratio is 1. Okay. Another possibility is that the adversary buys skis right away, in which case each time I rent, my ratio gets worse, right? So the adversary rents or buys, okay? But my claim is if it rents, then while I rent, the ratio is 1. And so it doesn't get better, right? It's always 1. Okay. And also, if he buys right away, my ratio keeps getting worse. As I rent. Okay, so whatever the adversary does, while I rent, my ratio just gets worse and worse. Okay, or it doesn't get better. Okay, so my ratio doesn't improve as I rent. Okay. Now, what about once I buy? Okay. So the adversary may have already bought, they may have been renting before, they may continue to rent, but what can I say about the ratio once I buy? Well, sorry, go ahead.
It doesn't like get worse.
Right, so my cost is now fixed. Right? The adversary might keep paying more. But it certainly doesn't pay less. It doesn't undo what it already paid. So what this tells me is that once I buy, my ratio stops getting worse. Okay. So putting this together, I find that the worst ratio is at the moment I buy. Right? As I said before, Murphy's Law says that the moment I buy is that is the moment that I break a leg. Okay? So if that's the case, right, if skiing stops the moment that I buy, on the trip where I buy skis, what is the ratio? How much do I pay, given my specified D?
D plus T.
Right, I pay D plus T, right? I rent for D days, and then I buy. Now, what does the adversary pay?
Minimum of D and T.
Yeah, or close to. I think it's the minimum of D plus 1 and T, because the adversary either has to rent, the adversary will either buy at the beginning and pay T, right? Or it will rent for all of the trips, but that's the D days and also the last day. Yes?
Right.
So it should be pretty obvious. I mean, now what's the worst ratio? Well, it basically happens when we balance, right? if D is less than T, then the adversary will pay D plus 1. And I'll have D plus T over, let me write that out. If D plus 1 is less than T, then my ratio is going to be D plus T divided by T, right? Sorry, divided by D plus 1. Right? Which is decreasing with, sorry, did I write? Sorry, fell off my notes. Hang on a second. Right, so if D plus 1 is smaller than T, then the worst case, sorry, having a brain moment. Let me start with the other side. So if D plus 1 is larger than T, that implies that the ratio is D plus T divided by T. So I can minimize this, which is what I want to do at D equal T and get 2T. If on the other hand, D plus 1 is less than or equal to T, then I'm going to be doing D plus T divided by D plus 1. And again, I can minimize this at D equal T, and I get 2T, sorry, I get 2 in the beginning, and I get 2T divided by T plus 1, which is less than 2. So what this shows me is that I should just set D equal T, right? And I achieve a ratio of 2.
Wait, don't you minimize D by setting it to T minus 1?
Oh, here? Yes, thank you. And so that gives me 2 minus 1 over T. Right?
Isn't the top one also minimized at D equals T minus 1?
No, the top one I think is minimized at T.
You should say D plus 1 is strictly bigger than.
Oh, you're right. Sorry, I'm looking at two separate, I'm double counting the cases here, right? This is for D plus 1 strictly greater than T. So I can't set it to T minus 1, right? But sorry, I've scrambled it up by trying to derive it. But the point is that if you set D equal to T, right, then you achieve a competitive ratio of slightly less than 2. Okay. And that is the best competitive ratio that you can achieve. Because we've also shown that the adversary will, like if you set D equal to T, then again, the adversary will break your leg when you buy on the T plus first step. And therefore you will end up paying 2T and the adversary will only pay T. Okay, so we achieve a competitive ratio of 2. Okay. Any questions about that? Okay, so that was perhaps the most basic online algorithms problem. Let's start to do a few more complicated ones. So let's think about selling something. Okay. So if we think about trading on the stock market, right, we've got some stock and we want to know when to sell that stock. Now, if we know nothing about the stock market, we're kind of doomed, okay? We can look at the price on the first day and, you know, we could sell then or not sell then. It's possible that on the second day, that stock becomes valueless. So if we don't sell it on the first day, we get 0, okay? And so that sort of, in which case we would have an infinite competitive ratio because we get nothing, whereas the optimum algorithm gets something. So that says that you have to sell on the first day. But if you sell on the first day and you know nothing about the market, then on the next day, the price could grow to an infinitely large amount. So that means that if you have nothing constraining the market, then you can't be competitive, okay? It's not, you can't be competitive. Okay. But let's suppose that we know a duration and also a max and min price that can be achieved for what we want to sell. Okay. So the advantage of this is, you know, we can look at that first offering price and, well, if it's close to the maximum, maybe we should take it. Equally important, since we know the duration, we can, we won't get caught out not having sold it. We can always sell it at the last moment for the minimum price. So I'm going to use capital M for the maximum price and little m for the minimum price. And I'm going to write phi for the ratio between them. Okay. And the key point is that we can always get M by waiting until the last possible moment and selling, which means that we can always get a ratio of phi, right? Because at best we can achieve capital M, which will be phi times little m. But the question is, can we do better?
Susie, just for clarification, the problem is that like we only buy one share at some point, or we keep buying.
So this problem is modeling where we already have stuff and we want to sell it. Okay, there's no buying here. It's just a question of when we sell.
Like we sell our whole amount of share in one.
Great question. So can we sell in pieces? And the answers are actually different for this, okay? So suppose the answer is no. We're selling a car, okay? Can't sell off one piece at a time. What is the best competitive ratio we can achieve?
I guess the phi.
What was that?
The ratio between max and min.
Well, we've already achieved the ratio between max and min, right? So we've got small m over here. We've got big M over here with a ratio of phi between them, right? Even if we sell for little m, that is a 1 over phi fraction of big M. So we're getting at least a 1 over phi fraction of the total. But the question is, can we do better than phi? Better than the ratio?
Can we get the square root of phi?
How?
I guess like if the price rises above like the geometric mean of the
Great. So what we're going to do is we're going to set a reserve price at the square root of m times m, right? So what that means is we'll sell the first time it's larger than that. Or at little m if it never reaches it. Make sense? So how do we analyze the performance of this algorithm? Well, case one, there's an offer for root mm, right? Well, we'll take it. And so we will get a ratio of square root of mm divided by the best possible price, which can be written as the square root of m over m, which is equal to the square root of 1 over phi, right? So we get that root phi ratio. Okay. Now the second case is that there is no such offer, right? But what that means is that the best offer is smaller than the geometric mean. And so our ratio is what we sell it for, which is m, divided by the best possible price, which is root mm, which again is root 1 over phi. So either way, we get within root phi of the optimum, and so this is root phi competitive. Make sense? Okay. Now let's revisit the question of what we do if we can sell in pieces, right? Suppose we're selling off peanuts instead of selling off a car, so we can sell a little bit at a time if we want to. Is there anything that we can do that we could take advantage of that in order to do a better, in order to achieve better performance?
I mean, maybe you could distribute, like, take the reserve price to the next level where you set waypoints, I guess, geometrically spaced between the two, and then
great. So, like, imagine, for example, making 2 reserve prices, right? So, if you think of the geometric mean as being halfway, we could look at sort of 1/3 of the way and 2/3 of the way, and have 2 separate reserve prices for the 2 parts, for each for half of our material, right? Okay, so for example, we could have a reserve price at m to the 1/3, big M to the 2/3, and also at little m to the 2/3, big M to the 1/3, and we can sell half at each. Now, what argument can we make about how well that does? Right, so again, now we're looking at, here's big M, here's little m, here's 2 separate reserves.
Like the third root of mn times half, something.
Yeah. So basically, we did a case analysis of 2 cases before. Now we can do a case analysis for 3 cases, right? The optimum price is in one of these 3 bands, right? So if the optimum price is in the middle, is in the bottom, then we're never going to sell until the last moment when we sell for little m, right? If the optimum price is in the middle, then we're going to sell half of our stuff at the lower reserve price, right? Because at some point we'll get an offer above it. And if the optimum is in the top tier, then we will sell half of our material at the second, at the higher reserve price, because again, some offer will be made above it, right? So at least half of our stuff is sold within the cube root of phi of the optimum, because some reserve price is that close. And that implies that we get a 1/2 cube root of phi competitive ratio by using 2 pieces. And once you've thought that through, it's pretty natural to generalize. Okay. What we do is we put reserves at little m, 2m, 4m, 8m, all the way up to big M. So there are log phi different reserves. We sell a 1/log phi fraction at each reserve price. Right? And we, again, now we can say that one of the successful reserve prices is within a factor 2 it's at least 1/2 of the optimum price, because these are distributed in powers of 2, right? So a 1/log phi, a fraction of our stuff, is sold at half the optimum price, which means that we have a log phi over 2 competitive ratio.
Times 2.
Sorry, times 2. Thank you. Does that make sense to everyone? Okay, so now let me go back to the car. Okay, I said you can't sell a car in pieces, but algorithmically there actually is a way you can sell a car in pieces, which is to use randomization. Okay, so randomization can often substitute for sort of splitting your choices, right? So we just looked at having log-free different reserve prices and doing a little bit of our selling at each reserve price. We can kind of achieve the same thing using randomization, right? So we can choose a random reserve price. From the ones listed before. Okay. And my claim is that there is a chance, namely a 1/log phi chance, that we choose the reserve price that is the reserve price R that is between half opt and opt, right? If we choose one of these prices uniformly at random. And if so, we earn opt over 2, right? So the expected earnings is equal to the probability that we earn anything times the amount that we earn. And so we have a 2-log phi competitive ratio in expectation. Make sense? All right. So that was kind of the end of the sort of elementary problems where everything was just about a number. Now we're going to start thinking about problems that have actual structure to them. So actually, I'm going to start with scheduling. Okay. We've already talked about scheduling problems where you have the entire input and you optimize some objective function. In scheduling, it makes a lot of sense to say that jobs arrive over time. And you have to assign a job to work when it arrives. Okay, but with that change in the sort of model of arrival, you can still use all of the scheduling structures that we talked about in approximation algorithms. So for example, I can still use the same notation, right? I can say, all right, I've got these parallel machines and the jobs are arriving over time. And as each job arrives, I have to schedule it on a machine. And I just want to get all the jobs done as quickly as possible. So can I, but now that again, I don't know what jobs are going to arrive when I'm assigning, right? When I'm assigning one job, I don't know what jobs might arrive later. So what sort of scheduling algorithm might it make sense for me to use, given that I have no idea what's going to come after?
Greedy.
Greedy, otherwise known as Graham's rule, because back in those days, you could get your name put onto an algorithm that was just the greedy algorithm, right? As a job arrives, you assign the arriving job to the currently least loaded machine. So how well does this do?
From last student, I think this is a too competitive algorithm.
Right. This is a too competitive algorithm because it's a too approximation algorithm, right? We showed that this algorithm achieves 2 times the eventual optimum, right? And if it's going to achieve 2 times the eventual optimum, that means that it's 2 times, that means that it's a too competitive algorithm. Okay. The point is that Graham's algorithm was always an online algorithm, right? It could deal with the jobs and it just sort of made a decision about each job in whatever order it looked at the jobs. And it didn't matter what order you looked at the jobs, you would still end up with a true approximation. And so by the same reasoning, you're too competitive against the best possible schedule. Okay. Now, Graham's rule was only the start of our approximation algorithms work, right? We also showed that if we did, or at least I claimed that if we did shortest processing time first, I claimed that if you schedule the jobs in decreasing order, you actually get a 4/3 approximation. And we also showed an enumeration-based algorithm that gives me a polynomial approximation scheme, right? So can we, lift these ideas and get a, 1+epsilon competitive ratio for online scheduling?
Not necessarily, because I don't think you get information about how big the next set of jobs is.
Yes. I mean, that is the point of online algorithms, is that, right, you don't know what jobs are going to arrive later. Now, why is that a problem?
Like, I guess an adversary could give you jobs in ascending order.
That's right. I can't control the order, right? So I can't use these because I cannot reorder the jobs, right? I can't do I can't schedule in order of decreasing probability, decreasing processing time, because that's not the order in which they arrive, right? If you think about the enumeration algorithm, right? The enumeration algorithm said, take all the large jobs and schedule them by brute force, and then put on all the small jobs. Well, what if the small jobs arrive first? I can't hold them in order to do the scheduling of the large jobs and then put the small jobs on. That violates the online algorithm specification. Okay, so I cannot use these techniques that look at all the jobs at once. Now, does that mean that this 2 competitive ratio is the best you can achieve? The answer is no. You can beat 2. Okay. So, I mean, Graham's rule was from the 60s, right? It remained the best known algorithm for this very straightforward problem all the way up until 1995. Okay. Bartal et al. Managed to improve the competitive ratio to 2 minus 1/70th. It only took 30 years, okay, to beat 2. How did they do it? Well, they did it by looking at what messes up Graham's rule. So does anybody remember how we made Graham's rule do badly?
I guess giving first a bunch of very tiny jobs and then a big job.
Exactly. What we did was we sent in a tremendous number of really tiny jobs, which Graham's rule was going to schedule evenly on all of the machines, right? And so it's basically optimal for this collection of tiny jobs. But then at the last moment, we would send in a job that was as tall as the average, and there wouldn't be any place to put it. So it would just have to be stacked on top, and that would give us our ratio 2. Yes? So Bartal looked at that and said, okay, we need to prevent the adversary from doing this. So what Bartal said was, we need to plan for the arrival of a giant job, right? And if you think about it, a pretty natural way to plan for the arrival of a giant job would be to just leave one machine empty, right? You could schedule all the jobs on the other machine, like all these tiny jobs, they would be a little bit taller if you put them onto n-1 machines instead of putting them on n machines, but only a little bit. And then when a giant job arrived, you could put it onto that empty machine. Now, it's not quite that easy because it's not clear what would be a giant, like how big would the job have to be in order for you to sacrifice the empty machine. So what Bartal did instead was they basically created 2 classes of machines, the large and the small. And they said, I'm going to have some machines that are slightly underutilized and some other machines that are slightly overutilized. Okay. And anytime a large job comes in, I'll put it onto the underutilized machine. And so it won't quite double the work of the worst machine, right? But when you do have a large arrival like this, you're going to change your thresholds for underutilized versus overutilized, right? You're going to take this machine now and move it over here. But now you've got a lot of, now you can actually declare all the other machines to be underutilized again. So they play some very careful balancing in order to make sure that there's always a set of machines that are slightly underutilized that can receive large jobs. Okay, so that was their brilliant insight on beating the factor of 2. And that kind of opened the floodgates. I was in graduate school at the time, and we looked at that and said, gosh, ought to be able to do better. What we should do is we should run sort of many groups instead of just 2, right? So you could have sort of the small, medium, and large, right? And we actually showed how you could construct a linear program to optimize the group sizes. So we have a computational proof of something that you can achieve. So whereas this 2 minus 1/70th is about 1.986, we were able to push that all the way down to 1.945. Okay. And then in 97, somebody else came along and pushed it down to 1.923. And after that, I got kind of bored with the problem and stopped paying attention. So I don't know what the current status is of the competitive ratio. These algorithms are all ugly. And so I believe in my heart that there is a beautiful, elegant, simple algorithm that does the best of all, and that has not yet been found. So that's, I think, an interesting open problem. I think, you know, additional tiny improvements that are based on messier and messier algorithms just don't seem that appealing to me. But if you could find that final elegant algorithm and close off this problem, that would be really cool. There are also lower bounds. I think it's known that you can't beat 4/3, for example, or maybe even 3/2. Okay. So any questions? So I've shown you a single scheduling problem. As I mentioned, just about every scheduling problem out there can be re-examined in the online setting. It's usually pretty obvious how to redefine it so that you have to place jobs as they arrive. So there's tons of online scheduling problems to work on if you're interested in that sort of thing. But that's all I'm going to say about scheduling theory. Are there any other questions about it? All right, so the last thing that I want to talk to you about today is to go back to that paging problem. But since we've been working for a while, let's take a 2-minute break so that everybody can stand up and stretch, and then we'll resume. Maybe I should solicit some appropriate algorithms music for our breaks. If anybody has any suggestions, I'm happy to hear them. All right, so let's talk about paging. So I already introduced this in the context of memory and disks, but it's actually more general than that. There are many places in our computer systems where we have a small fast memory and a large slow memory. Okay. And obviously we want to access information from the small fast memory, but it's small. So we have to decide what to keep where. And we have to move it around as needed. Okay. Now, the sort of relative costs, the difference in cost between these memories can be huge, right? It can be factors of tens or hundreds or even thousands between your fast memory and your slow memory. So even one access to slow memory costs a tremendous number of, is as slow as a tremendous number of accesses to fast memory. So, you know, if you're going to access slow memory, you want to make it count. So what you do is you divide your memory into pages. Okay. And when you need the memory on, when you need something on a page, you fetch the whole thing. From the slow memory. Because these slow memories tend to have terrible latencies, but decent throughputs. So if you're going to get one thing, you might as well get 1,000. Okay. So for example, you know, with disks, the page size will often be several kilobytes or possibly even several megabytes. So even if you're just accessing 1 byte from the disk, it will haul in kilobytes and kilobytes of data, because doing that is no slower than just getting 1 byte of data from the disk. And the hope is that you can rely on locality of reference, right? That if you're going to be accessing one thing from this page, you'll probably be accessing other things as well. All right. So each time we need to fetch a page from the slow memory, or sorry, each time a memory access is unavailable in the fast memory, we have what's called a fault, or a page fault, and you need to get it from the slow. And the problem is you have to make room for it, right? The fast memory is small, so you have to evict some other page to make room for what is needed. Okay. And so the algorithmic question is, what page do you evict when there's a fault, right? When there's a fault, you know what page you have to get. So the only flexibility is, what do you get rid of to make room for it? And as I said, there's many layers of this in modern computer systems, right? You've got the main memory versus disk. You also have cache versus memory. And in fact, modern computers often have 3 different layers of caches. So the L1 cache is quite large and quite slow. The L2 cache is smaller and faster, and the L3 cache is fastest of all, right? Or sorry, I think I said that backwards. And then you've also got the registers, right? So some data is stored in machine registers and can be accessed with, like, there's no cost to accessing that at all in your processor. So there's lots of reasons to be able to solve this paging problem, okay? So suppose this happens, right? You're running a paging algorithm. You get a page fault. You need to evict something. What should you evict? What would it make sense to evict?
Like, I guess the page that we use the least amount of.
Okay, so there's least frequently used, right? We could keep track of how often we fetch each page and, sorry, how often we access each page, and drop one that we don't access very much, right? Any other ideas?
Least recently used?
Yeah, so this is something that computer scientists often look at, right? So we can keep track of when we accessed each page, and we could evict the one that has been accessed the least recently, the oldest page. Any other thoughts? Well, some other possibilities, we could do FIFO, right? Like you evict the pages in the order that you got them, right? We could also do LIFO, last in, first out. This would speculate that we got the good stuff early and we want to keep it. Right? There's one that we haven't talked about because it's not actually doable, but suppose that you were gifted with the gift of prophecy. What page would you want to evict?
The one that's accessed farthest in the future.
Exactly. That's actually what it's called. Farthest in future. Okay. This is also known as Biloti's algorithm. Because again, in the old days, you could get your name on anything. So the question is, how well do these do? How can we analyze them? Okay. So it turns out that Biloti's algorithm is actually optimal. This is what you should do. Okay. The problem is that it requires knowledge of the future. Okay. These other algorithms, however, do not require, the other algorithms are online. And the question is, what can we say about their competitive ratio? Okay. And it turns out that, unfortunately, least frequently used is not competitive. And neither is last in, first out. However, least recently used and FIFO are both K competitive, where K is equal to the number of pages that you can fit in your small memory. Okay. So that's the crucial parameter, right? How many pages fit in your small memory? And we have these two algorithms that have that parameter in their competitive ratio. Okay. So let me first show you an easy argument that these algorithms are K+1 competitive. Or actually, I'm going to focus on LRU. You can go back and analyze FIFO the same way. Okay. So suppose that I break any sequence of requests, of page requests, into so-called phases, where a phase ends when there's a K plus first new page request in the phase. Okay. So I'm going to assume for simplicity that the caches initially start out empty, right? Ours and the optimum. So I'm going to watch the request sequence, and at a certain point, there'll be a K plus first page requested. And I'll say, okay, that's the end of a phase. And the next request I'm going to count as the start of the following phase. Okay? Now, what can I say about a phase? Remember that our goal here is to compare the performance of our algorithm, LRU, to the optimal algorithm. So what happens to LRU in a phase? Oh, sorry, I misspoke. It's not k+1 new page requests. It's k+1 faults. Okay, by LRU. So then the answer becomes sort of obvious, right? If the phase involves k+1 faults, then LRU has had that's what LRU has had, right? But why did LRU have k+1 faults? Well, the point is that LRU only faults on a page. Or sorry, let me put this another way. LRU only evicts a page when it becomes the oldest. Right?
Excuse me, can I ask a question?
Yes.
You break the sequence of page requests to like, so that the number in each phase can be larger than k+1 of page requests.
The number of pages may be large, right?
Okay, so you wait until like k+1 faults happen and then put that in the whole sequence of requests to a phase.
Correct, but sorry, I think I see I want to be careful here. Let me think for 1 second. I think I may have dropped a bug into my notes. Pages. Yeah, okay, good. So so we're taking this phase where we kind of end the phase on the k+ first fault, right? Now my question is, if there are k+1 faults, what can we say about LRU? Okay, how can these faults happen? All right, and let me turn that backwards. Okay, my claim is, if the phase only has k distinct pages, what can I say about LRU? Right. How many faults can occur if there are only k pages in the phase?
Most k.
How come?
I think it's because you'll never get rid of one of the k pages.
Exactly. Right. So if there are only k distinct page I should say page requests as opposed to pages, right? If there are only k distinct page requests, then none of them becomes the oldest, or becomes old enough to evict. Right? These will be the k youngest pages, and so they won't fall out. Okay, so that tells me that a phase has k+1 distinct pages. Okay, but if there are k+1 distinct pages and there's only k space in my small memory, what does that tell me about opt?
There's at least one page fault.
Right, right. Opt has a fault. So in each phase, LRU has only k+1 faults. Opt has at least one fault. So we get a ratio of k+1. Okay. Now that's a very simple argument, and it's almost tight, but I need to refine it slightly because the actual tight answer is k. Okay. So the refinement I'm now going to consider a phase ending on the k plus first new request for a page, not new fault, but new request. Okay. Now, if there are k plus 1 requests in a new requests in a phase, then LRU is going to have k faults, right? For the same reason as before. Okay, that none of these requests are going to be evicted before, like none of the first k requests are going to be evicted. So you won't fault them more than once, okay? But now let me move the first request of each phase
Excuse me.
Yes.
Shouldn't it be k plus 1's page fault? What do you mean by new request?
No, I'm giving a different definition of a phase now, right? So new requests are requests for pages that have not appeared in the phase. Okay, so again, I start with an empty cache. I start watching the pages that arrive, right? And when the k plus first page request arrives, that's going to start a new phase. Okay.
Okay.
So what that tells me is that within a phase, that there are only k pages. And that means that none of them will get old enough to get evicted, which means that each of them will only fault once, which means that LRU will only have k faults. Okay. So now what I'm going to do is I'm going to take that new page, that request of that request that started a phase. In other words, this k plus first page, this k plus first new request of the previous phase. And I'm going to move it into the first, into the previous phase. This is just for accounting. Okay. So essentially, if my sequence of requests was something like this, and k is 3, so if I have a sequence like this, so my phases will take 3 new, we'll look 3 pages at a time, but I'm now going to adjust the phases so that I take the first request of each phase into the previous phase. And now what can I say about opt on the new phases? Well, what I can say is that the rest of the phase has k requests that are distinct from the moved page. You know what? I see I've gone over time. I want to respect that. So I will pick this up next time to show you the sort of completed, to complete this proof that we are k competitive. All right. So as usual, look for a problem set to be posted, which will be about geometry and online algorithms. And I will see all of you on Friday. Okay.
Thank you.
Sure.